Okay, so my name is Grant Reeves. I am a pre-med student, neurobiology major at the University of California, San Diego, and I am studying for the MCAT with the 2019-2020 Kaplan Complete 7-Book Subject Review, and this is the first chapter of the General Chemistry book. So, we have sections 1.1, 1.2, 1.3, and 1.4, and we have learning objectives in all of those, and that's what I'm going to be going through. So, our learning goals, learning objectives for section 1.1 is to identify the subatomic particles most important for determining various traits of an atom, including charge, atomic number, and isotope. So there are three things identified here. We got charge, right? So the most important thing in determining charge is going to be the electron, right? So because the number of protons doesn't change and neutrons don't have a charge, electrons are going to be the thing that determine the charge, because an atom can easily gain or lose electrons depending on how much energy is present. So the atomic number is going to be the protons. The atomic number is a measure of how many protons a particular atom or particular element has. And an isotope, that's neutrons. The thing that changes when an isotope changes is the number of neutrons. Different isotopes have different atomic masses, and so when one carbon atom one carbon-12 atom has an atomic mass of 12 AMUs, a carbon-14 atom has 2 extra neutrons, which makes it a different isotope, which is the next learning objective. Determine the number of protons, neutrons, and electrons within an isotope such as carbon-14. So protons don't change ever, or it would act as a different element. So 6, because there are normally 6 protons in a carbon atom. Electrons also going to be 6 because there is no charge on this particular carbon-14. And neutrons, normally there would be 6 to bring the total to carbon-12, but carbon-14, so we have 2 extra neutrons, so we're going to have 8 neutrons in this particular carbon-14 atom. So, section 1.2, atomic mass versus atomic weight. So, describe atomic mass and atomic weight. So, atomic mass is the particular mass of an atom or of one isotope, right? So, an atomic mass can vary between isotopes. And atomic weight is something intrinsic to a particular atom, which is the average of all of the different isotopes of that atom. So recall the units of molar mass. So molar mass is how much a mole of a particular element weighs. And now we recall that a mole is 6.02 times 10 to the 23rd things. Like just how you can have a mole of donuts, you would have 6.02 times 10 to the 23rd donuts, right? So recall the units of molar mass with their grams per mole. Predict the number of protons, neutrons, and electrons in a given isotope. So we kind of already did that. Given any isotope, you would look at the atomic number. From that atomic number, you can calculate it out, basically. Anyway, so 1.3. Calculate the wavelength of an emitted photon given the energy emitted by an electron. Okay. The wavelength of an emitted photon given the energy of given energy emitted by an electron. Okay, yes, the wavelength. So this, you can use the E equals hc over lambda formula. So h is Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. And c is the speed of light, which is 3.00 times 10 to the 8th meters per second. And lambda is represented by wavelength. Lambda is the Greek numeral for wavelength. And so you would calculate the wavelength emitted by the photon by plugging in your energy, and then you would multiply your you would divide your energy by Planck's constant and the speed of light, and that'll give you your wavelength. Excuse me. 2. Calculate the energy of transition from a valence electron that jumps energy levels. So this one, you're going to use your energy equals R8, negative RH brackets 1 over n initial squared minus 1 over n final squared, close bracket, and that is the combination of two previous formulas that we see in in section 1.3, which is L equals n over h, n h over 2 pi, and E equals RH, negative RH over n squared. So yeah, I basically plug in the different energy levels that you are swapping from. Those are n, those are your shells, and RH is the Rydberg constant, which is 2.18 times 10 to the negative Rydberg unit of energy, excuse me. Yes, Rydberg constant, which is 2.18 times 10 to the negative 18th joules per electron. So yeah, I believe that's it. Oh, and calculate the energy of a photon given its wavelength. That's the same thing. That's easy. You just plug into the energy equals Planck's constant times speed of light over wavelength. Given the energy, Planck's constant and speed of light never change, so plug in the wavelength and you have your answer. Section 1.4, quantum mechanical model of atoms. So objective number 1, identify the 4 quantum numbers and the potential range of values for each and their relationship to the electron they represent. So you have 4 different quantum mechanical numbers, quantum numbers. So you have N, L, ML, and MS. So N is represented by integers, and that is your shell. That is, if you think of the Bohr's model of the electron with the central proton and then different electrons orbiting around the outside, this is what orbital you are in, right? L, suborbital. That's S, P, D, and F. It's Will. It's my roommate. Right? You'll notice that those also correspond to different areas on the periodic table. That will be helpful when you are determining the number of valence electrons that a particular element has, or isotope or anything. So ML is the orbital. So this is going to be represented by a denotation of a number next to your 1s, 1p, 1d. Get that? So representation for something like hydrogen would be 1s1. It's simple. 1 electron, 1 orbital. It's the simplest one. So then ms is your spin, and remember that when you are making a diagram, an orbital diagram, you will always have one arrow going up in each box and one arrow always going down in each box. And this is because of the spin. That's referring to the spin. So it's, say again, you have 1s1, and that can have a plus 1/2 or a minus 1/2, right? So plus 1/2 spinning upwards, minus 1/2 spinning downwards. Yes. So going backwards, compare the orbital diagram of a neutral atom such as sulfur, S, to an ion such as S2 minus. So in order to do this, you're going to need to be able to calculate the number of valence electrons in a particular atom. So let's take a look at sulfur, like it gives us the example. So sulfur has an orbital diagram of neon, right? So you're going to write out the noble gas that is closest to it. And then you're going to have 3s2. I dropped my pen. So anyway, so you're going to have 3s2. And then you're going to have, 2s2, sorry. 2s2, and then 1, 2, 3, 4. Then you're going to have 2p4. So the difference between that or a -2, sulfur -2, would be that you would have neon, 2s2, same there, and -2, we know that electrons have a negative charge, and so gaining electrons is going to give you a more negative charge. So this particular sulfur atom or ion is gaining 2 electrons. So it is no longer 2p4, it is now 2p6. So differentiate between paramagnetic and diamagnetic compounds. So paramagnetic refers to the attraction or repulsion from a magnetic field that a particular compound will have. So if there is a metal that has half of its d orbital filled, meaning half of its valence electrons filled, that means that each orbital will only have one electron in it, because remember Hof's principle, I believe it is, that electrons assemble in elements like they would if they were on a crowded bus. Everybody wants to sit in their own row, and it's not until the bus is too crowded that they start sitting in seats right next to each other. So, paramagnetic basically means that something is attracted to a magnet. Diamagnetic means that something is repulsed by a magnet. I think of this as paramagnetic, there's only one. Diamagnetic, there's two. So you can think of it like people. If there are two people, they're already paired up, and then there's another magnetic force over there, then it's a loyal electron. So the electron is already loyal to its other person, so they're like, no, be gone, thought, and so it doesn't want anything to do with the diamagnetic, doesn't want anything to do with the magnetic field. Paramagnetic, attracted to a magnetic field. Diamagnetic, repulsed from a magnetic field. That's just how I think of it. It's funny. Determine the number of valence electrons in a given atom. Okay, so this one you can just observe in your periodic table pretty easily. So you could take any example. Let's go for carbon again. I guess we've used this one before. So each shell, when you go from one shell to the other, valence electrons refer to the electrons in the outermost shell of a particular atom. So in carbon, a particular carbon is going to have 6 electrons, but 2 of those electrons are on the innermost shell. They're 1s shell. I'm just looking at the example that I used now for sulfur, and I'm realizing that those were both supposed to be 3s instead of 2s, but it's okay. The example kind of works anyway. The principle works. I just had a brain fart. So there are 2 on the inner shell, right? So you have your proton, you have 2 electrons orbiting around, and then outside that you have another shell that can be filled by 6 electrons, or 8, I believe, actually. Yeah, it's 8 electrons in the second shell, but yes, it's 8, excuse me. And there are going to be 4 electrons in that outermost shell. Yeah, you can just count that over. So it goes lithium, beryllium, boron, carbon, 4 atoms in the outermost shell of 4 electrons in the outermost shell of carbon. Okay, and that's it. And then it just goes into the concept review in the book. So, good deal. There's chapter 1 of the general chemistry review.